Thank you. Mo, you're up.
All right. All right. Thank you very much, guys. And I'd like to thank all of you for the opportunity to also present, and thank you for also inviting in the future. Yes, across the Bristol Channel, I used to go to a university named Cardiff, so I do plan to visit at some point, and I would like to drop back whenever your next meeting turns up. All right, so today I've called this resin creep and fastenings and ways to avoid failures. So what I'll walk you through is a little bit about the durability of concrete structures as a primer. I don't intend it to be a full sort of lecture from a structural engineering perspective, rather just to orient ourselves about how our most common base material into which we install resin anchors, epoxy anchors. They go by different names, and I tried to really standardize as much as I could, but bear with me. They're all sticky substances, and which we put in some steel elements, and we try to make sure they last for a good number of years against different weathering conditions. However, they are impacted by creep, and we shouldn't be afraid of that. All materials are, and it's just by proper qualification, assessment, and design. And of course, nothing is complete without a good installation. We're able to mitigate any of those risks that show up. So I'll spend a few minutes orienting, on durability, as we mentioned, and what we want from structures is for them to last a certain time frame. So they must be durable against a certain set of loads that they'll act upon, for a certain service life against the prevailing climatic conditions. Now, there's no equation here, so you can't just put in a bunch of numbers and crunch it out. A large bit of it is based through structural calculations, prior investigations, prior knowledge. That's the main thing here, and a combination of other nebulous things which cannot be quantified in a mathematical equation. Out of which, if you use the BSEN 1990, you get a certain number of indicative service life, which might not always apply to all types of structures, particularly nuclear ones. I understand it's a bit different, but anyway, the durability and the structural resilience of most buildings is captured, irrespective of which design standard you follow. So the demand of this, again, comes from different projects. So for a common building, this is typically slated at 50 years. And for certain projects, it can be 120, 150 and beyond. I haven't seen much from 150 and beyond, so that's just there as a placeholder for now.
You are muted. Yeah, let's try it again. Amol, you're muted. Amol, can you hear us?
Can you tap the keyboard with that function?
Sorry, Amol. Can't hear you.
Better now?
Yeah, you're muted. Just, I don't know whether we
just rewind now 2 minutes.
Yeah, the previous slide, we can maybe go back. Sorry.
Also, yeah, can we remove this back?
Was it here? Was it here, or are we good?
We finished this one. Yes.
Yeah, we finished this one.
All right. Let me start through again here.
Yes.
Okay, so durability also falls under the greater umbrella of service conditions for structural design, and this follows the limit state philosophy. We're not going to walk through every single limit state, but essentially any building must do one of two things: ensure safety under the worst possible loading conditions and not undermine the appearance or performance of said structure. And under serviceability, we have a bunch of different conditions. So deflection, which is the appearance or efficiency of any part of the structure. You should not be adversely affected by deflections, nor should the comfort of the occupants. Imagine the room you're sitting in, the beams above start deforming a bit unpleasantly, so not something we want there. Cracking must be controlled within a certain limit, and of course the big one we come into is the durability one, and this has everything to do with time. So you'll notice time is a common theme throughout this presentation. Hopefully you're not watching your watch, but yes, that's the main thing for all building structures. Vibration, fatigue, and fire resistance, I won't walk through them, but essentially they're key to ensuring serviceability is maintained. And I think this you will recognize. I took it out from the new civil engineer. This I think is of the project you're working on. Hopefully you have all of this in place and much more. All right, so another way to think of durability is any resistance to degradation, in the sense that the structure must remain fit for purpose over a specific time period, after which you can replace, you can refurbish, do whatever you want with it. However, it is not a good substitute for maintenance or inspection. Regular inspection must still be part of any sort of maintenance protocol for the life cycle of the structure. Concrete structures and their individual elements do deteriorate over time. There are many ways of how that can do it. Generally, it's water that's going to cause the main issue, and this leads to corrosion of the reinforcing element. There are some other things like the chemical reaction, freeze-through or fire, and all the other nasties that we don't want, really. And the deterioration is not as big a common factor from chemicals, but anyway, we can talk about that later. So if there is a problem with durability, because it's down to this corrosion in steel, you'll notice on the right-hand side that as the corrosion initiates, afterwards to collapse, there's a very rapid growth, and this can lead to, if you don't observe it, it can lead to some catastrophic results as well. So any sort of premature degradation, you can have a bunch of pattern defects, and also serviceability and the premature end of service life. And if that doesn't happen, definitely increase maintenance costs if you account for the life cycle of the project. Okay, that's enough for the durability in concrete. Let's move on to a little bit of creep. And durability is also impacted by creep. Now, this is on the loading side. So all of that was from the material side, and what happens when all factors are plugged in. And the creep is a bit different. So this is again based on loading over a specific time. And what better way to illustrate this than, allow me to transport you from the room you're in now, a nice comfortable room, to a glacier in the Alps. And what you should see is the movement of glaciers over time as fresh snowfall pushes the ice further downhill. And you might be thinking, what does that have to do with creep? Well, it's the exact same condition just seen in nature. Another way to look at it is through fault mountains. And so essentially we're looking at a slow, continuous deformation that's based on time, and it does not happen instantly or with a variable rate. Now, you can think of it as, and I can challenge some of the audience in the room, just a very quick question, a very big show of hands. I can see all of you as well as those online. Do you think this happens all at once or uniformly? I can repeat the question if you like, but does creep happen all at once or uniformly?
Hands up for each one.
Hands up if it's uniform, and hands down if it's all at once.
I say uniform. Uniform.
All right, thank you for that. So it's a bit of both, depending on the stage you're in. So let me plot it. It's a good way to satisfy all parties, right? Just say
Everyone.
All right. So vertically, let me put it on the vertical axis. If I look at deformation, you can see how creep starts rapidly and slows with time. That's horizontal. And let's call this stage the primary stage of creep. All right, so this is when you initially load something. It's a beam, it's a slab, or anything of the sort. It's pretty much rapid. Then we move on to a sort of steady, deforming ever so slightly based on the load over a much longer period of time. And this is the most predictable for a material. And we return to this a bit later because it impacts how we assess epoxy anchors here. And finally, or beyond a certain point, the deformation intensifies and this culminates at rupture. And as living things, as we cannot escape aging, so too is with materials that cannot escape creep. So it's, if you want to use a better analogy, I can't find one, but I welcome you to come up with one. Okay, so the consequences of a continuously applied load over a long enough time span become fairly evident. And you could argue that if loading is below a certain point, as is the case of suspension bridges, which are lightly loaded over a longer time, and they're only stressed rapidly and occasionally very rarely, then you can have structures that last a very long time. So a combination of loads, the duration, and the temperature really does affect how much they're going to deform. So this is true for any material. And what changes based on the material composition is it's what type of material do you have? Like, is it concrete? Is it a steel element? Or are we talking about structural timber? Are we talking about plastics, polymers, any other material that's being used? This is the main variable. And you can combine it with all the others, and the combinations are sort of infinite. And for polymers, I'd like to show what happens as the deformation or the rate of creep sort of increases. And this is courtesy of the University of Swansea. Here you can see the different sorts of individual polymer chains. Let me play that one again, as they slide against each other, leading to a certain point after which they will fail. Right. So that's one example there. And let's dive into now the world of the sticky substance, right? Resins, epoxies, polyester, polyurethane. What are we talking about here? Well, we're really not talking about the organic sort, so that's the gums from trees. Thermoplastics, so things can be melted, injection molded, formed, what have you. Let's ignore that too, as the majority of stable resins that we wish to use for structural applications are thermoset. So they're normally liquid with one or two parts, with a hardener or a filler that go in, and the epoxy structure on the other side. And once you inject them, they become solid. They stay solid up to a certain temperature. And this is where we find our three friends, the polyester, the epoxy, and the polyurethane. Why do we have three? Well, because the first one, the polyester, is, let's say, the grandfather, or sort of like the first one that was developed by the chemical industry in the last century. So it's a bit brittle, it needs reinforcement, and it's mostly used in sailing boats today with a bunch of fiberglass. So epoxy, this is what we're interested in, and this becomes more solid and stable once it cures. So it's perfect for use in many industries, including construction. And polyurethane, this is the most recent one coming out of the chemical industry. It's very versatile. It's used in foams such as the cushions and the seats that you're probably sitting on, the rubbers, the hard plastic that forms all our modern industry. So let's focus on the epoxies and the polyurethane just for a second. And what I want to show you here is epoxies have a linear curing time for working. That's roughly about 30 to 45 minutes, depending on whether it's fast or slow cure. And sometimes you can have the full curing developing in about 1 hour or the full 24 hours. It's again dependent on temperature. It's very linear. It's very steady. It's very predictable. And they deal very well with moisture. and they're very good corrosion resistance, often higher than the concrete or masonry and even structural timber. They're also very easy to use and are forgiving, not requiring many complex instructions for mixing and use. What about polyurethane and urethane in general? Well, it has a few differences. So the curing has higher variability, and you can think of it like a hockey stick curve. Nothing noticeable first and suddenly it cures. Bam. It's going steady, and then before you know it, it's gone. So they're not a big fan of water. So if you look at most compositions out there, you add a bit of water, a few drops, and most of these would start foaming, and you need a completely dry surface prior to use. They're also a little less forgiving when installing as well. So because of this, nearly all resin anchors used in the industry for fixing are epoxy based, and of course there are other types of fixing, such as mechanical anchors, but those we don't cover today because they follow the creep behavior of a metal, so that's steel and stainless steel, to be specific in some cases. So where would you see these? Of course, in the building you're sitting in, other vital civil infrastructure. They all used post-installed epoxy anchors, and you'll find them in different types of fixings, whether it's connecting steel fixings such as base plates, rails, tracks, what have you, or it's connecting two concrete members together. So when you find them being used in structural fixings, then they must last as long as the life of the structure itself. Some others, though, such as the crash barriers, the noise barriers, and some MEP installations, these could be taken down. They might have a different service life than the main structure. So even within the project, you're dealing with a few different types of service lives. Oh, another sort of leading question, if you don't mind. Can any epoxy resin be used in construction? Or specifically for fixings?
Yes, answer.
Depends how you use it, doesn't it? So.
Okay, it's a bit rhetorical, but it's best I don't answer that yet. Yeah. Okay, so I took some inspiration from Mike's previous presentation. I saw bits of it. Thanks so much for that, kind of setting the stage for it. And about 2 weeks and 17 years ago, so on the 10th of July, so not finished the 17th anniversary, a massive section of the tunnel roof at the Fort Point Channel Tunnel in Boston collapsed, often known as the Big Dig project because of how expensive it was at the time, but that's a story for a different day. So as the anchor bolts ripped loose, so you have about 24 metric tons of suspended panels crashing below, injuring the driver and unfortunately killing the passenger. But bear with me, I have some, this is leading somewhere, and the NSTB report, so that's the National Transport Safety Board, the accident report here highlighted that the epoxy anchors installed overhead underwent creep deformation and fracture that led to a specific collapse. All right. That's what it looked like. Luckily, it was not a progressive collapse, and because the way these were installed, only a section of them unfortunately fell at the wrong place at the wrong time. And one of the things I used was the epoxy selected initially did not have any evaluation for creep resistance under sustained load. And so if you look at the way they were secured, these pretty heavy concrete panels, it's a typical overhead installation where you're basically suspending concrete slab using a turnbuckle and anchoring these in with the chemical system. So the safety issue report that came out of it, some of the safety issues that were highlighted were that the chemical anchoring was insufficient, that there were insufficient understanding of the chemical anchoring systems amongst designers, and there was also lack of testing under sustained tensile loads. So this report also acknowledged that the installation was generally inconsistent with the manufacturer's recommendations. However, this was not the only contributor to collapse. So a bunch of factors came together, and that's what generally happens in these big collapses. So at the time, though, there was just a simple pass or fail criteria to assess creep in under sustained loads in epoxy anchors, where if an epoxy anchor passed that criteria, it would have a lower safety factor applied on the loading, and that was pretty much it. So the report and the consequent findings were of great importance, and I'll show you how they fed into some of the anchor testing protocols that we have today. So a lot of things have been mitigated, and the report that came out has been extremely helpful in that. So if we fast forward to 2012, a similar collapse occurred, but this was a much older tunnel built in 1977, 80 kilometers west of Japan, west of Tokyo in Japan. And here we had a lot of factors again coming together: load fatigue and material creep of the early chemical anchors. These may have been of a polyester type. It's not 100% certain what types they were. And unfortunately here, it was unlike in Boston, this dia section was, there was no redundancy built in, let's put it that way. So once the collapse occurred, it was pretty severe, and it claimed 9 lives, so more severe. So there were a bunch of factors, even in the design and construction stage. So some of the adhesive bolts did not exhibit a specified pull-out strength. In addition, the action of the loads and material over 35 years deteriorated, and at that time, I'm pretty sure there weren't any creep testing regulations for epoxy anchors. So afterwards, what happened is that Japan kind of banned everything in overhead tunnels, or basically overhead fastenings in tunnels, and I'm a little uncertain whether these have been relaxed in recent developments, but yes, that's how severe it was. So what happened in both failures? Essentially, we had a loss of adhesion. So this happens when the epoxy starts to display uncontrolled slip and pulls out of the drilled hole. So you saw some of the pictures in the previous slides. Essentially, what's happening is that at this red circle along the graph is when things start going sideways. And the long-term displacement behavior of the load displacement curve, but this depends significantly on the irregularities in the drilled hole. So if you're doing hammer drill, you want to make sure that the drill bit remains in tip-top shape most of the time. And the bond stress at or the load at which it starts failing, and that's over here, this is known as the loss of adhesion. So the question again, leading, but again rhetorical, so no need to ask. So should we disallow fixings, or should anchor testing become more rigorous? And it has become more rigorous because these types of anchors bring a host of other benefits. So mitigating the risk of creep. So one of the things which came out from the tunnel thing was, how do you assess and quantify the degradation caused by creep? Right. So everything can be quantified, and therefore it can be designed for a certain time frame. So previously, the erstwhile criteria, the E-tags also, basically they had this pass-fail criteria. So nothing really in the design itself, unless you use the American ACI 318, which applied a de facto 55% of the initial load. So basically, it kind of penalized you if you used the chemical anchor. That's it. Irrespective of the chemistry of the anchor, of the epoxy, doesn't matter. You used it, you suffered a penalty. Fast forward to today, where we have the Eurocode 2.4, which is, I think in the last 5-6 years been developed, and a lot of that uses design parameters that are coming out of the EAD. Now, what is the EAD? I'll talk about that in the next slides. So that is the assessment criteria. The EAD is the assessment criteria. There is a specific one for bonded anchors or epoxy anchors, as you know them, for use in concrete. There's a separate one for use in masonry. There's a separate one if you're connecting two concrete elements together. This one is specifically for base plates and single point fastenings. As a result, you'll get a unique ETA that comes out of this. So again, depending on the application, depending on the base material, you'll get a different output or so, a bunch of data. This data is then fed into the design method, and an engineer can design with it, specify it, and therefore it can be installed according to all the specifications mentioned in this ETA. So all the leaflets you see for installation, they basically derive from the documentation in the ETA. So just to go through some of the testing here, so we're looking at a way to test creep in a standardized manner. So we can kind of evaluate how they will function over a service life of 50 years, 100 years, and such. Anchors are installed through various means, hammer drilled, diamond cord, so they're assessed in a standardized way. And what we're trying to determine are multiple parameters, such as reductions in bond strength, deformations, anything else that may affect the service life of epoxy. Essentially, what we're trying to prevent is a loss in adhesion. Here's a quick overview of the test setup. I won't walk you through this. It's really not that tedious, though. It's just basically you load it up to a certain load level, maintain that load level for 3 months, and then extrapolate it for 50 years. And if you're doing it for 100 years, you basically maintain that constant loading for about 6 months, and then extrapolate the displacements and the loads. Don't worry so much what it looks like on the right hand side. Essentially, the mathematics behind it is a power law for 50 years at standard temperature, 10 if you're elevated temperatures, not really talking about fire conditions here, but we're just mentioning about, for 40 degrees Celsius, if that's temperature of the base material. And there are some criteria, which the epoxy must display. And after which, these are pretty stringent. They might look that, oh, you can just have extrapolated displacement not exceeding the initial one, or the residual load being of a certain value from the initial one. But these are not easy tests by any means. Now, the fundamental assumption, which is why I walked you through the stages of creep earlier, was that we assume that the behavior, like for all other materials, remains the same for the epoxy as well. It's in the secondary stage, and therefore it's predictable, it's steady, and usable from a design perspective. The next we work on is the ETA itself. I'll highlight certain sections and what this document really contains. So if you look at the opening page, it will show you which specific type of fixing it's meant for. Is it meant for base plates to concrete, or is it meant for concrete to concrete, or timber connections? There's even one for that, and other things as well. So under the specification of the intended use, this will always be standard for any ETA you might pick up. The left-hand side one is specific to HILTI, but there are others as well, which will have the mention of for how many years is the assumed working life, so for 50 or for 100. Now, again, the assessment is unique to the anchor, unique to the fixing, and contains the data and the manufacturer's instructions as well. So if you flip through this, you'll find a bunch of data, right? None of it is super relevant at the moment, but let's have a look at what the initial bond strength can do and how it degrades as you start going further down this document. So initially it looks pretty nice, pretty high values, and then you start dropping them down with reductions from the concrete itself. And the last one, this is the one we want to focus on as a designer. The data you get out of this is then finally quantifying it from a design perspective. And this must be published for all tested service lives. Whenever you're assessing or seeing the equivalency of one a mortar with another or one epoxy with another, this documentation should show you and give you the requisite data you need to say, okay, I have a certain epoxy I'd like to use, and does this have the right data? Is it assessed for a certain time frame? And can I use it for the life cycle of my project, or do I need to replace it after X number of years? Last on the list is the design method. I won't walk you through it, but basically all the data we got goes into 2 or 3 very simple calculations, which are run by a software in the background. So any designer, even anyone in the audience, can basically sign up and start using it anytime. But where it specifically impacts and starts degrading is the group bond resistance. So there's a specific failure check for that. There's a bunch of failure checks as indicated here, but what we're looking at is the impact of REAP is over here, the combined cone and pullout failure, also known as the bond failure. And you get a parameter, this size sustained, which then basically drops your performance. And this can then be quantified based on how much loading you have, and therefore gives you a very good idea over the service life, how well your anchor will perform, or how well your group of anchors will perform here. Lastly, though, we'll wrap up with quality execution. Now, all this design is rendered useless by subpar installations, and vice versa as well. You can have no design, no proper installation can be fixed from a poor design. So even assuming those 2 failures earlier were designed incorrectly, no amount of good installation would have saved those lives. So the right selection involves the right anchor with the European technical assessment that's specific to the application, specific to the service life. So if continuous loading is expected on the fixing, which is almost certainly the case in most scenarios, then your anchor must be selected appropriately. And avoiding epoxy anchors would definitely limit their flexibility and the host of other benefits they bring, both installers, contractors, designers, and the entire project team as well. And the right design aims to ensure that whatever loading conditions are present on the job site, they're accounted for, and it's good practice to assume that all these fixings will encounter sustained loads over their life cycle. So it's good practice to generally take these into account. And following the correct installation, we want to make sure that the design and installation is done reliably, and there are a bunch of tools that can help you achieve that, and make sure that the installation works for however long you want it to. And lastly, the verification with proof tests at a specific location or a bunch of locations is a good option to verify correct installation. And I'll end with this, and I can leave some questions open here. So the main thing is to, like all materials, expect that epoxy anchors will undergo some sort of creep and deformation, but as long as it's quantifiable, it's assessed and designed for, so that there's a lot of ways then the risk can be mitigated as long as the holy trinity can be followed: selection, design, and installation. And I'm open to questions.
Thank you, well, that was fantastic, really enjoyed that, and you know I'm interested in this anyway, and yeah, it was really good. It's nice to expand on my very basic, for God's sakes, don't do this lecture. It was lovely to actually someone to present the science and we can understand that. That was just fantastic. Thank you very much for that. It's wonderful.
Yeah, I want to second that. But we've advanced from don't use to here's the solution, design, and the other 2 points of the triangle. I can't remember. Yeah. Can we go online for questions? Is there anybody online that would like to ask anything first?
Just something in the chat, let me open it up and see.
Okay. No.
No questions.
No questions. Okay. I won't put anybody in the spot. Online, if you've got any questions from Paul and the team here in the room, feel free to pipe up, raise a hand or whatever, but we'll go to questions in the room for now. Around the room, any questions?
No, for me, it was just.
It's quite important, sorry, go on.
No, you carry on.
I was just saying it's quite important at every stage, from the design to the suitability to the training of the people that can install, to the whole system. We know this from the tool to the anchor to the design, the actual looking after the product itself. We sometimes don't look after as well. So either temperature controlled or life cycle of the product as well, rather than just picking up a tube of, you know, epoxy as we always used to for temporary works.
It was the magic key, wasn't it?
It was. And I think it's just having that respect at every stage. There's a lot of work goes on in the background, I know, and it's just highlighting to the guys at the front line, the importance, because it can have the effects like we see at the start in those tunnels.
Yeah, the quality of the installation is everything, isn't it? So
Definitely. There's some couple of weak links in there, isn't there? A missed design code or a missed installation. The product is past its shelf life, or it's been frozen, or it's been too hot, or
whatever it's putting it in or another.
It is, you know, I think there's a respect at every step of that way, isn't it?
Yeah, exactly, yeah. Especially after all that work's been done to certify the product and test it, and yeah, it can be spoiled by something relatively minor on site, which is not what you want. Experienced operatives installing this is super important.
Just asking, those two failures, it's in any way linked to HILTI, or they're just in general epoxy business?
Actually, none of those two were HILTI products, but it's also, we need to be clear that this was in both of those cases not necessarily a product or manufacturer problem in all these cases, and I've said it a few times, but it's a culmination of multiple oversights, let's call it this way. And then that also combining with the lack of regulation or testing and approval processes in the back end, that really combined into pretty catastrophic circumstances. But ultimately, this is, of course, and this is why at the end it's about installation. This is really important because, and you said it rightly, Amol, that so firstly, no poor design can be fixed by good installation, but likewise, no good design is worth the money it's written or the paper it's written on unless you install it correctly, right? So it's really something that needs to get together. There's a lot of call it meat built into all of these things. I mean, even if you look at testing data that you get in an ETA, even with reduction factors, it has some meat, right? So there's always a little bit of room for things that just naturally happen on job sites. So we never have to be scared of doing using these systems, because we think that job site conditions are just too unreliable or not possible for you to predict. Those job site conditions are considered in the data that you get, but ultimately due diligence in design, due diligence in selection of appropriate products with data, and due diligence with installation has to come together. Otherwise, you will not be certain.
Yeah, as Amol said, we wouldn't bore you with the whole contents of the MTSB report from the Big Dig collapse, but there was a litany of many small failures
Yeah.
that led to the product failing in the end. And it wasn't just one thing that went wrong, it was about 5 or 6 things. And that's the reason it failed, because there was lots of problems, oversight, lack of installation, quality, and all sorts of other stuff. And it's never, as Emil said, it's never just one thing. It's normally like a washing list of stuff, and then you get a failure.
Yeah.
Does that answer your question, Bill? Thank you. So when it comes to those failures, it was a case of back then, those tragic events, it was misunderstanding and misapplication and a whole suite of things that went wrong.
And lack of understanding of the product, because the product at that point, you can draw parallels with, asbestos and all sorts of stuff. They didn't really understand the product, and as time goes on and experience is gained, you do understand the product, but often it's at the mercy of, or at the cost of a life loss or something like that, and that's the wrong way to go about testing the product. Well, sadly, that's the way it is.
Using Resin Anchors 25 years ago, and the salesman that came down to explain it to us what they were was just effectively telling us it was magic in a can. He just really sprayed it in there and sort it all out. And unfortunately, the driver, sales being the driver, was promoting that. So there was a lot of misunderstanding in our industry in the UK about this, that it was magic in a tube and it would do everything, and really it couldn't.
No, that's right. That again is like a product understanding. I was super fortunate. 15 years ago we started to use this. One of the members of our team was Dr. Donald Pearson-Kirk.
Yeah, we met him, didn't he?
Yeah, he came, and he was the guy they called when those fell out the ceiling to find out why it went wrong. And it was, working with him was an incredible privilege. And he also managed to, rather like Mol, set the scene for exactly what went wrong and what we had to do to stop that going wrong. And it was pretty interesting, and a lot of the stuff, almost all the stuff I know about it, I learned from Donald. So
the other good takeaway from that is, although the loss of life is tragic, it's led to the investigations that have led to the understanding that's led to the regulations, that's led to our ability to safely apply resin anchors in the proper design scope to make sure that we have no further loss of life, hopefully.
Yes, well controlled in this country.
Yeah.
Well controlled. So
There's two other parallels that I will just want to draw here. So the first thing is the aviation industry, and the aviation industry does a pretty great job at understanding when things go wrong and then making changes to that. Construction is a little bit slower, but in this case, this was one of those catalyst effects that made suppliers, manufacturers aware of potential issues, and then led to us addressing these things. And also, if you think about fire protection, I mean, fire protection in the UK is also catching on, and in the US a few years ago it caught on, and unfortunately in those cases it was the same thing. There had to be people who unnecessarily lost their lives in fires in buildings due to improper fire protection and compartmentation, and as a result regulations changed over time, and these things happen, right? And I think Amol put it really nicely, is that we have a choice at the end of the day. Either we say we don't use these things and hands off completely, or we respect it for the benefits that it brings us, and just treat it also with the respect that, yes, certain limitations can be designed for, predicted, and overcome. And this is really what for us as well, it's a big thing for us. I mean, imagine we launched RE500 a couple of decades ago, and then all of a sudden realizing that maybe some stuff was not correctly addressed. So I mean, we have an obligation as well, and this is also where HILTI is pretty straightforward with these things. We have an obligation to provide you with systems that work under the conditions that we specify, and this is what we're trying to do.
So you mentioned the UK catching up on fire rates. Something that's very interesting is the government have revised the Part B, fire regulations for building. So yeah, we are catching up.
I remember when we first started using the RE500 for the Highways Agency for gluing in, we tried various other products to glue in rebar, and it was, we drilled them into a concrete barrier laid on its side and then did pull tests on it. And the others pulled out, and the HILTI RE500 pulled a core. The resin never failed. So after that, that was supervised by Dr. Pearson-Kurt. That's testing as well, and that was all they would allow. Highways Agency would only allow that material to glue in rebar, nothing else. And yeah, it was. I've never seen anything like it. You know, a bar under 25 mil would stretch and break. And when you get up to about 30, eventually, although it stretched a bit, obviously, it would pull a core. The resin would never fail. And that was, you know, that was absolutely shocking to see how good it was. But again, it relied on the operatives being properly trained to install it, the hole being rough enough, the moisture being correct, and all the rest of that. Because if any of those seemingly inconsequential things went wrong, it wouldn't work. So it was, you know, really tight control on site, and that's, you know, that's really what's needed. And that's where, you know, Clerk of Works can really help to understand the product, how it's used, and make sure those controls are in place.
Installation as well, to make sure that those steps are followed. Yeah.
I think just for practitioners in this industry, the installation piece, I always, in every visit to job sites or to contractors, I hear the challenges about the skill levels of the installers of these types of products, and the challenges with just having peace of mind that it's done correctly. And I mean, not only HILTI, but manufacturers and OEMs in this industry that do what we do are really trying to bring systems that are, on the one side, less, let's say, sensitive to real world conditions. And this is what you will find. I mean, we now sell your RE500 V4. Fourth generation of this product, right? And we are in parallel doing the next generation already. So it's always with the intent of making more robust to real world conditions, but at the same time, the installation of these systems, we're trying to make it simpler. For example, cleaning. I mean, you know about these things, but mitigating the need for cleaning by using systems like dust extraction while drilling, or the likes. And you know, this is what we're trying to do, and this is also something that as practitioners you have the ability to say, let's supervise more stringently the process, or alternatively, if the contractor choose, there's also other means to ensure reliability of installation by maybe using more advanced systems. Things that may have been available already 10 years ago, but have not yet been adopted necessarily by the greater construction community. So it's always, and this is where we try and help, because we know as good as you that the installation is one of these key little rings in this chain that has to be done correctly.
Yeah, I think we've, you know, by testing and your perseverance with the product and massively improving the product, you know, the shift in failure modes has drifted back to the installation now. You know, that's pretty much the only place it can go wrong, because we've got controls for the design, controls for the product, and, you know, the last place that we need to shine a very strong light on is making sure that the installation is correct. Because the rest of it's very well proven now.
So to drive that, yes, exactly what Clerk of Works do is check, and check.
Yeah, and mentor and stuff like that.
Yeah, drive continuous improvement. Exactly. There's a number of things that Clerk of Works do, and importantly, we can make sure that side is kept to a minimum through experience and.
What we do with HILTI points is we provide nuclear anchor training, for example, with certificates. But there's still a discussion with some of the tier 2 contractors, you know, saying, well, we've done this job for 30 years, I don't need nuclear anchor training. I've got knowledge and experience. But when it comes to our experience was on the job site, okay, we appreciate you've got 20 years experience, so we let you do the demonstration and installation. And as we're trying to go through the steps, just bear with me, please. you need to do this. Okay, then, no, please. Okay, you do the demonstration. And it's surprising though, with people with a lot of experience, there is still sometimes, you know, and I think this is how you change that mindset of someone who's done it for many, many years.
The coaching and the training.
Yeah.
You guys have worked all that many years. Point of failure, isn't it? Point of failure is the human.
Yes.
It's the installer. And that's really, like you say, with clerk of works, we have to have witness points, we have to have hold points. But we really need to train and empower and coach in such a way that those guys who've got that experience, or the new guys coming up, standardise that, because you spend all that money doing that. Let's spend some money here.
Yeah.
You know, so let's spend some money at the fault place.
And it does make sense, you know.
Yeah. When delivering the nuclear anchor training at the beginning of the year, I found two things quite interesting. First of all, actually the installers and workers, they appreciated to get a context of the theory, because we explain why anchors fail, how they can fail, and what are the things in installation that can make them fail. And they actually appreciated that knowledge, that learning. But also when we're doing installation, as Paul says, especially the more experienced ones, they realize that for years they've been cleaning the holes wrong.
Yeah.
Small things like that they think they're doing it right, but not quite.
Yeah.
So
to reiterate on that, Sandra, sometimes they've been taught wrong, and other times they've never been taught. They've never read the manual. They've never done it.
Yeah, exactly.
Yes, about more than 25 years ago was my first day on site, and not long after that I probably used one of the first my HILTI products. No one never actually told me. I was actually reading in very bad English that time, you know, and some German understanding, and actually how to apply that product. And actually the biggest resistance always been in any trainings and everywhere. You can see it from the people with long experience. They know what is right. And they quite often, if you analyze some failures, there will be some people with long experience, with long old school methods working, and they don't want to adapt these technologies, adapt the lessons learned.
There's a lot of areas like that with the rebar couplers as well. You have to have many standstill moments to say, right, where's our risk in our installation? When do we have to have some enhanced training? You know, identify those who are grip tech coupler people. Now, like HILTI anchor people, we need to, you know, those who go up and down on the meet, we identify those. All these at-risk places, we need to really identify those and give it the same sort of respect that you guys have done as well.
Because keeping the product to tolerance so it lasts is super important.
Yes. I mean, Devon Taiwan had a great initiative to provide like these modules, the training, you know, these short videos, 1-2 minutes long, which are available for people to look at as reminders. And I think that sort of stuff is brilliant. You know, it's a great thing.
I think I was down, we've got an immersive training centre now, down at K23. So it's a classroom probably about the size of this. There's a little auditorium where you sit on there, but the whole room is 3, 4, 5 projectors all around the room. When you just go around the room, you touch the wall on certain things and it opens up. So our new induction is going to be down there. It's going to have hazard spotted. I was down there the other day, there was something about the Egyptians. You learn all about the Egyptians or an aquarium. But it might be that we use that room for the quality and sort of advanced training like this, to put people in an immersive zone in the safety of a learning area as well. But what I'll do is when we're out and run with it properly, if you wanted to, one night we could have the meeting in there. Cool. An immersive night in the immersive zone.
The only limitation we've got is about it being on site, but I think if we let everybody know that only badge people can come, fantastic.
Yeah,
well up for that. Thanks. Yeah, we can get more visitors, but what fun is anybody just turning up, obviously, but you're right, with notice we could do that.
Or we could just do it during the day, you know, we can have an afternoon session there just during the day. We want to come and have a look at the bylaw in new induction in the immersive centre, and just have a look, and then perhaps we can use the immersive centre for other things going forward, for different kinds of learning.
Excellent. Thanks, Alex, that's absolutely spot on. So, an opportunity for our guest speakers to plug. You've got design for these anchors, your design house or design software or design team. Can you talk around that for us, please? Available for everybody in the world?
Yeah, I mean,
That's
that's
maybe
worth about this. Or more you would like to know?
Yeah.
Something?
Yeah, sure. So the design software is available for anyone to register. And once you register, you're able to access a way to simply design any HILTI anchor solution that's available. And yeah, it's pretty straightforward, and we can train you on the theory behind it as well. There can be a follow-up sessions if you like. I'm more than happy to do this one again in conjunction with Paul and Sandra.
Yeah, and the good thing about it as well, it's available online, so you don't have to messing about with IT, you don't need to download things. I know sometimes the client can be quite specific about which software iteration to use, because sometimes, you know, the software has to be validated and verified. So there's a desktop version as well available, which is Process Engineering 2.8 or Process Anchor 2.8.
No, we have a Process Engineering version now. So Process Anchor was the old name of the software. Now we have Process Engineering, which is cloud-based. It's online and anyone can use it. And there is a specific desktop version that has been approved by EDF in France that can be used for Hinkley Point C and other EDF design. It just has to be made available through a special link.
So I think what we can do just in practical terms, I mean, whoever is in attendance tonight or anyone else who is interested from the chapter, we can share just a link to where you can register. Registration is very quick and simple, and then it's available to everyone, right? And everything that Amol showed today can be applied by anyone with a technical understanding of how to just run step by step through a typical anchor design. All you need to reflect on is geometry. Yeah. So it's really simple, and like I said, registration is very simple online. Easier than connecting to this facility's Wi-Fi.
Quicker. Now. So just to clarify then, so for the benefit of people online and for the recording, this shameless plug of Design Tech is available online. You don't need to download anything, so it's available on online server, and it's called HILTI
Process Engineering.
Thank you very much.
We've got 100, it's like design in the bathroom. We've got 100 registered.
And you now design anchors, but also concrete to concrete connections, so rebar connections with the same software.
Thank you very much. No, I'm just very cautious that we're recording and there's multiple people speaking at the same time. Alex, I know you're speaking.
Sorry, Scott, I was just speaking to Paul there, and he was saying we've got 100 registered users in our bio temporary works team. Already using this for our works.
Wow, that's a success in its own. That's 100 people using that. That's brilliant news indeed. And another opportunity for you guys to get a shameless plug. The FP700, is that something you wish to talk about as an injection?
It lends itself quite nicely not to talk about it. Thank you.
Yeah. Thank you. Thanks for bringing this up. So yeah, FP700. I mean, we've been talking a lot about epoxies tonight and how epoxies behave under these conditions. FP700 is exactly the opposite of that. So FP700 in a nutshell is the first and the only injectable inorganic mortar. So it is a cementitious injectable mortar, the same packaging as RE500, and we use the same dispensing guns or glue guns to dispense them, right? And why did we develop this? It has one superpower that nothing else in the industry has. It's also patented this way, but it performs like concrete under fire. So when you elevate the temperature in epoxies beyond 100 degrees, it starts to melt. I mean, it's a very fancy plastic, right? But FP700 can withstand temperatures like concrete up to 500 degrees Celsius. So under conditions where you need to do post-installed rebar connections in a plant where your structure has a fire rating of 1, 2, 3, 4 hours, often when you design it for those elevated temperatures, no chemical anchor will work, and now we have the solution for that. And that's its superpower. That's what it's designed to do. Obviously, inorganic materials are also useful for other purposes. Yes, it performs really well when it comes to creep, so it does have good creep behavior, but this is not a creep product. It's a product for fire. And that's FP700. So if you ever need, and it's highly likely that you would,
we will do it. It'd be very interesting to see what the new Part B regulations say about that.
Yes.
I think that's worth us having a little exercise to look at that.
You know, it's always interesting because this is very new for us as HILTI. It's a new technology, completely patented and all these sort of things. So we're stepping into a new playing field. And I visited the US, I visited India, I visited the UAE, visited Belgium, France, all digging into this specific topic. And, you know, every code globally that deals with structures are clear about fire resistance of concrete structures. It's very clear, right? There's not a single code that we've uncovered that doesn't explicitly require the resistance of these structures in the event of a fire. What's also clear is that if you simply do a one-to-one swap between cast-in rebar and a post-installed rebar, you have problems. So you have to redesign them, similar to what we described today with creep. It's not impossible to do, but you have to consider the fire case in the design. And if you don't do that, you could have a situation where you have a problem. What's nice about FP700 is the design is not at all affected by fire anymore because of its performance. And yeah, this is FP700 launching next month.
Yes.
Next month in the UK, so it'll be available. It'll be available for sale within about 1 month from now. And in the meantime, you can start specifying it if you like.
Okay, well, for the benefit of the recording, you heard it here first.
Fantastic achievement, it's fantastic, well done.
Okay, I have one more thing to discuss, and that is the excellent discussions that we've had and the questions and conversation in the room, just as informative as the excellent and amazing work that Amol did in putting together those slides. But what I would like to say is, or ask the question, will you guys from HILTI and Gal from HILTI be interested in supporting us with our Recorder magazine with some content for us around this subject? We're talking 1,500 words, double pager. Would you be willing to do that with some insight from us, myself and Alex here for guidance? But we need content for our magazine, so I'm groveling again. Not only have you supplied a great lecture, but we'd like to share that knowledge with our wider institute. Are you able to help us with that?
Sure, yes.
We'll give you a few back copies of some of the magazines, you know, the last few months to get an idea of the content that other people have done before. That would help.
I'll share them with Paul, and Paul you can disseminate.
Is this where you tell me we need it by next week?
No. Not at all. I was in a communications club meeting with the ICWCI. And I took on an action that I really regretted because
this is delegation 101.
Yeah.
2 weeks.
Maybe I junior.
Yeah, go ahead.
So I think Paul and Sandra, you might want to speak to Laura and Carlos. I think they'll be more than happy to co-author, and we can always find people from the BU. The business unit who can help you with specific topics.
Absolutely, yeah. Once Paul gets the past issues, we can get an idea of the type of content, and I'll speak to our colleagues locally, Laura and Carlos, and we'll see what content is available if we need to make something bespoke. Because I know that on topics like process engineering, there's already some papers that have been done as well. And on this specific creep topic, I'm not sure, but then we can discuss what's the topic that we want.
Perfect timing would be the revised Part B regs and your products around that. So maybe a deep dive into the revised regs.
And we're very happy to do something on fire for sure.
Yeah.
We want fire.
Absolutely.
We're really keen on fire because that's the buzzword at the moment.
Yeah, we're very happy to work on something with fire for you, no problem. And any other topics, like I just also wanted to mention that, like, I mean, we are here from headquarters, and we are really keen on the work you do, and I mean, we really love the project and what our team did here, but it's really about the relationships that we have with you. But we also wanted to emphasize that we have a very strong team in this part of Europe. It's called E1, and their hub is in GB in Manchester. And there we have a very strong technical team as well to be very close to you on a consistent basis. I mean, for us at headquarters, we are involved with selective topics where we can and where our capacity allows. But you have a team here that supports consistently and regularly from Manchester as well, which obviously Paul has already been orchestrating for the last 5 years. So but we just wanted to emphasize that, right?
Thank you. Thank you, Jan.
Thank you. I just wanted to say thank you very much for all of my former colleagues and now my friends from HILTI for coming and giving us fantastic insight into the products and how they're used. And I've spent the last more than 20 years working with some of your older colleagues from HILTI on various projects, and the support you've given me has always been first rate. So thank you very much.
Thank you.
Can we offer our thanks in the usual way, please?